Next point we're going to mention for internal energy is a way to kind of think about it. Another way to think about it is that internal energy is something called a state function. And a state function means it's something that really doesn't matter the pathway, how you get there. You only need to know the initial set of conditions and the final set of conditions. So for this case, well, how much energy did the system have to begin with, and how much energy did the system have to finish, end? That's all that matters. It doesn't matter the pathway. That's what a state function means. You only need to know the beginning and end conditions, not the pathway. So internal energy is a state function. But these two guys, the heat involved in this process and the work involved in the process, those both are not state functions. They are path dependent. And one way to kind of think about this, which may or may not make sense, is say you were going driving for a long distance, and we'll say Denver, Colorado. It's always easy one to go to. Denver, Colorado. Okay, as far as your elevation goes, you have an elevation known in Canton, Michigan, and an elevation known in Colorado. You could take many different routes to get to Denver, Colorado, and change elevation several times along the way. But if I simply ask you, what is your elevation change? You would measure what it is in Canton, and you'd measure what it is in Denver, and that's all you need to know. Different set of circumstances. If I ask you how much gas you use on this drive, in other words, the heat or the energy, you would definitely need to know a lot more information, the pathway you took. Did you take the most direct route, or did you drive all over the country before you actually got there? That would not be a state function. That is path dependent. So the route you take is important. You have to know the route for Q and W. But for the internal energy, you don't need to know. All right, let's move over and do one of our problems in our homework. Start off with number 8. It mentions for number 8, there we go. In the accompanying cylinder diagram, a chemical process occurs at constant temperature and pressure. Is the sign of W indicated by this change positive or negative? So I guess the very first thing we need to do is make a couple little drawings here. So I'll do that. Cylinder number 1 and cylinder number 2. We'll pretend these are the same. And then you have an initial volume in this cylinder of 4 liters. And then after some pressure has been applied to this system, pushing the cylinder down, we get a new volume in here. Okay, so looking at this. Is the sign of W indicated by this change positive or negative? And let me give you another formula before we get too much further. W, in regards to work pressure, pressure volume, is set up by this equation here. So the change in volume of the cylinders and the pressure that is placed upon them to have this done. So pressure is placed in it and the change occurs in volume. This this negative sign here is only there to kind of fix the signs. We get a positive value out of this or a negative value out of this, depending on what's happening. It doesn't have any other indications, just to make the sign the way we want it to be. So is the sign of W by this change positive or negative? So the volume went from 4 down to 1 liter. So the volume went down. Well, let's write this down here. So we're at constant pressure. So we have constant pressure on the outside, yet this changed. Constant pressure on the outside. So some work was done on the system. So at constant pressure, the volume decreased, right? We can see that went from 4 down to 1. So the volume decreased, which indicates a negative sign. It decreased, it went down, it's negative. So therefore, if this causes a negative value at constant pressure, we can ignore it. That means the overall work is positive. Okay? B, if the process is endothermic, so maybe you know what that was from last year, or if not, we're going to talk about it right now. If the process is endothermic, does the internal energy of the system within the cylinder increase or decrease during the change, and is the change in energy, internal energy, positive or negative, right? Well, let's discuss. Internal energy is the sum of Q plus W. We already discussed in the previous problem that W is positive, and if the system is endothermic, I'll just write endothermic, endo, Q is positive. Endothermic means energy goes into the system. We're adding energy to the system. So that is positive, and W is positive. The sum total of those will make the delta E, therefore must be positive. Done. All right, let's bounce back over to our notes and talk a little bit about what that delta E meant. Wrong paper. So for enthalpy, that is a new word. It's the first time we've actually referred to it, enthalpy. Enthalpy, it stands for, or is, H. That's the symbol we're going to use for it. And it is E plus pressure volume work. But it's under constant pressure. Okay, well, if I'm under constant pressure, what are we really talking about here? Well, we know from the previous problem that we just talked about, this is the formula for pressure volume work. We'll just kind of restate that. This is the work done by the system. In other words, that's work that leaves the system, which is why we get that negative sign. And if I want to look at a change in enthalpy, we're kind of deriving this formula. Change, we're going to look at delta E plus P delta V. So we're putting changes in for this equation there. And now we've got some things that we can actually incorporate into this equation based upon some things we've talked about in the last couple of problems here. Delta E is equal to these guys, and this I can put in place for W with a little bit of changes on it. So let's do that. Enthalpy, delta H, I'll go ahead and rewrite that in here, is equal to Q plus W, which we're getting from up here, minus W, which we're getting from here with the addition of the negative sign, incorporating that in there. Therefore, enthalpy really, under at constant pressure, we're just looking at that as heat, the heat energy in a system. We can ignore the work that the system does under constant pressure. And just to mention something else about enthalpy, it also is a state function. Okay, this is a pretty good place to take a break, and we'll start on lecture number 3.